be in an area where you already set aside for some other data or instructions.
And that's why there's a RAM N+1 there.
Yeah, here you go. So the safest place is to put it close to the end of the RAM, because you've
Mm,
already not reached the end of the RAM by writing any program. So you know for sure that you are far away from the end of the RAM.
right.
So that's why we select the end of the RAM. That's the whole philosophy. But the stack theoretically could be anywhere, as long as you make sure that it's distant from where you're working.
Right.
And so now we are executing this instruction. The original instruction we are executing is the here branch here. This is where we are right now.
Okay.
What are we waiting for? We are waiting for this interrupt. We are waiting for this event, the hardware event, which is going to change the world here, change the status of the machine. And look at that. It's going to push the status of the machine somewhere else, and then start going to somewhere else, transfer control to somewhere else. So many things are going to happen once the interrupt takes place. How do we know that an interrupt how do we know that the interrupt is taking place? The big event we're talking about is the interrupt, as a matter of fact. Here you go. So where we are here, yeah. We are here. So, all right. So an interrupt will take place. How does the machine know that it has to go here? The interrupt request is activated, all right? We know that the interrupt request is activated because you already pushed the switch. Once you push the switch, the machine is already configured for the non-maskable interrupt level triggered. So the program counter knows where to go. So the program counter is going to go automatically here. FFF2. What is FFF2?
There's a
This is the
location.
interrupt vector. Go back to the interrupt vector.
Yeah.
But as I said, this location is generic. In your case, go to the real interrupt vector. The real interrupt vector. It's I recall it's page 365 of the in the book. All right. So that means you're starting to play with the interrupt service routine. You're starting somewhere else now. You're gonna go to the interrupt service routine. So org FFF2, you're transferring controls to somewhere else in the RAM, and then you define something called interrupt request, interrupt service routine. All right.
What is DCW again?
Define constant.
Define
Word.
constant word. Okay.
Yeah.
Yeah.
Interrupt service routine. So automatically that's gonna take you here to the label called interrupts requests dash interrupt service routine. This is the beginning of the interrupt service routine. This is the interrupt service routine. It's between these these 5 instructions actually, starting
Professor,
from
I have
load
a question.
accumulator all the way up till return from interrupt. This is our interrupt service routine. So now let's see what's gonna happen during the interrupt service routine.
Professor, what does the temporary define?
What does what? I'm sorry?
At the beginning of the code, there is a temporary define constant bit 1. What does that do? Like, what's the importance of that?
It shows you the label that we are jumping to. This is where we are jumping.
Not that at the beginning, before the entry load S.
DCB1, the
No,
one that says temp
forget
DCB1.
about this one. This is a reset vector. We are not resetting the machine now. We want to go to the interrupt service routine. So we know the interrupt.
Professor, he's talking about this one.
I'm sorry?
That one. That one. He's talking about that one.
We're talking about that one.
Yeah.
F2.
No, this one. That's what he's asking. The temp DCB1.
The first line.
This one. The one I'm checking right here.
The label. This is the label.
Yeah.
This is the label. This is the label that you are jumping to.
That one. Temp DCB1.
No.
That's what he's
We're not.
asking.
We don't care about that now.
Oh no? Okay.
No. We're doing this. We're gonna go back here.
Okay.
So we're gonna load accumulator A with temp. What's in temp? Nothing. It's cleared. So as
Yes.
if we're saying load accumulator A with 0.
Are we saying that temp is equal to like 1 bit or something? Is that what it means? Temp
It's a
DCB1?
variable. It's a variable.
It's a variable. Are we like
It's a byte. It's a
defining
byte.
a constant 1 byte?
No,
Okay.
It can't be 1 bit. It's a byte.
1 byte. Okay, got it.
Yeah.
Okay.
It's a byte. Now we load accumulator A with temp. What's in temp? Go back here. Temp is already occupied by nothing. Clear temp. Remember?
Temporary storage.
Yeah, clear temp. Then you exclusive OR accumulator with this.
Toggle bit 4.
What does that mean? All we are trying to do is change the value of bit number 4 in port B. Remember, we are changing the value of bit 4 in the accumulator. We're not at port B yet. We are still in the accumulator. So we're exclusive OR the accumulator with this. What does the exclusive OR function do? The exclusive OR function finds the complement.
Okay.
If you were storing 0 in this location and you're exclusive ORing it with 1, the result is going to be 1. So the 0 will be converted to 1. So as if you're you're negating B4. Bit 4 in the accumulator is negated or is going to be replaced by its own 1's complement. Do you see? So this is the accumulator. The accumulator is already in temp. Temp is carrying 0. So we're replacing 0 with the exclusive OR here. So you're going to have B. Look at this comment. Exclusive OR 1 with B4 is going to give you B4 bar. Why are we doing this? Because the goal is to toggle the LED. Before we toggle the LED, we want to toggle the bit in the accumulator first, and then we're going to send it to the LED. We cannot have access to the LED directly. We have to have access to the accumulator first, and then you're going to deal with the port that's connected to the LED via the accumulator. But you cannot talk to the LED directly. You have to talk to it through the accumulator. All right. So now, exclusive OR, and we stored it in temp. We stored the accumulator A with temp. So now, accumulator A, if accumulator A bit 4 was 0, which means the LED was off. If accumulator 4 bit 4 was 0, it's going to become 1. If it was 1, it's going to become 0. Whatever it is, this is a general case. Whatever was in the accumulator to start with is now going to be 1 complemented. You're going to get the negation of it here in temp. And then you're going to send it to port B. So the original value of port B,
Yes.
the
Goes up.
original value of port B is now going to be complemented. If port B was, or line 4 was originally 0, it's going to become
Be
1.
one.
If the original one was 1, it's now going to become 0. Right? This is actually the end of the interrupt service routine because that's the goal. The goal is to toggle the bits, and then you say return from interrupt. Now, what's going to happen as you return from interrupt? Huh?
Is
You're
it?
gonna, you're gonna go back here.
And it's gonna go in a loop, right? Like
This
infinite
is
loop
what.
or something.
This is where you're gonna go to. I'm highlighting it already for you. If you return from interrupt, you're gonna go back to the endless loop where we
Yeah.
existed before the interrupt takes place. You see? Yeah. So now what have we accomplished so far is changing the value of port B. All right. Now let us read those comments. Pressing the switch will blink the LEDs. Okay. Pressing the switch will blink. If the switch is kept activated, the LED keeps blinking. Okay. Why does it keep blinking? Because you are already continuously pressing the switch. You are working in the level triggered mode, and in the level triggered mode, you have a continuous press on the switch. If you have a continuous press on the switch, you're working in the level triggered mode, and the switch is always 0. If the switch is always 0, that means you are continuously requesting an interrupt. Do you see the point? If the switch is continuously connected to logic 0, that means you are